But as I said, this is just for your sort of information. It has nothing to do with the subject, but it is important to introduce you to this subject as such. Anyway, so let us sort of get back to what happened. Can you? Oh. Can you see the screen, all of you?
Yes, sir.
And you can hear me, right? So before we start the subject of enzyme engineering, let us do a very, I have previous classes I have learned this very through unfortunately, that we need to sort of revise previous courses, and you have all done a course in reaction engineering, right?
Yes, sir. Chemical reaction engineering.
Yes, sir.
या तो केमिकल रिएक्शन इंजीनियरिंग आपने किया तो वही तो वो उसके बेसिक्स तो इसमें भी यूज होंगे ना सो वी विल आल्सो यूज द बेसिक्स ऑफ केमिकल रिएक्शन इंजीनियरिंग इन आवर enzyme engineering, because after all enzymes are what? Enzymes are essentially biological catalysts. So you will have more complex reaction mechanisms, but essentially they will be reactions. And so reaction engineering forms the basis of any such course, because only the fact is that instead of working with simple reaction models, we will work with more complex reaction models. And then, of course, unlike a course in pure enzyme kinetics, which is just talks about the kinetics of the enzyme rates, we will now be putting them in reactors. So the kinetics and the reaction engineering will combine to actually give you what is the end product, which is what you need to know. So quickly to revise it, there are essentially three types, and let me sort of, and essentially batch and continuous, and continuous has two types. Again, the ubiquitous CSTR, and of course the plug flow reactor, which is actually makes much more sense if you think about it, and I will talk about that in a minute. So batch and continuous, so these are the three reactors, and essentially all. Can you all hear me? Because it says bad network quality.
Yes, sir. We can hear.
Oh, okay. So hopefully you can hear me. If you can't, please sort of, I don't know, say something, okay? So that I will, it says bad network quality, so I don't know. I hope you can hear me. I don't want to restart the computer. Essentially, as you all know, that the essential material balance is accumulation is equal to input minus output plus minus reaction. If it is product, it would be plus reaction. And if it is substrate, it will be minus reaction, because substrate will be consumed and product will be formed. And so in a typical batch reactor, where there is no input and output, the batch equations would be essentially accumulation is equal to reaction, which is what which most biologists tend to get confused. They write first order reaction dC by dt is equal to Kc, which is not a definition of first order, but actually a material balance, because accumulation is equal to reaction. So it's actually dC by dt is equal to, or if it's nth power, this case, so it's actually accumulation dC by dt as represented by dC by dt is equal to reaction, which is actually represented, I mean, this is common sense, but I just want to sort of, is reaction dC by dt, and they are equal only because input and output are zero. And this is only true for batch, and dC by dt is by definition first order Kc. This is by definition, therefore 3 lines, and this is the material balance. So this equation captures two things, one a definition and one a material balance, and it's only true for batch reactors, right? Similarly, I mean, you could have anything, the reaction could be any Rx. So essentially the batch reactor balance is dC by dt if C is the component of interest equal to Rx, and Rx can have anything. It could be equal to Kc, it could be equal to Kc raised to n, it could have the asymptotic reaction, which is very commonly found in enzyme reactors, which is that they are first order in the beginning and they become saturated at the later part. And in enzyme kinetics, we write it as Vmax, which is really the maximum value here, but it is not really important, into S, where S is it could be C, if you would not write C upon K plus C, right? This ensures that this is 0th order when C is very large with respect to K, and when it is very small with respect to K, it is first order. So this is all these saturation kinetics, as it is called in chemical reaction engineering. So most of these follow saturation kinetics. In enzyme kinetics, we call it Michaelis-Menten kinetics, but essentially it is saturation kinetics. Why is Michaelis-Menten kinetics the same as saturation kinetics? Is something we will talk about when we go ahead in the course. But essentially the material balance is this, which may be equal to anything. The Rx may be equal to anything. And I can think of all kinds of complex things. I can put it restore of n, which is, Hill equation. And clever things. So whatever be the Rx, as far as my material balance is concerned, this is the material balance. And of course, in a CSTR, equation is more interesting and complex. Okay, I will not use C, I will use S. The reason I will use S instead of C is primarily because in enzyme engineering, S is the more preferred version, because really enzyme kinetics is S going to P, S substrate going to product, rather than C going to, or A going to B, or whatever. A going to B, or we write dA by dt. So instead of A going to B, we write S going to P is a more preferred option. So it's just a matter of nomenclature. Allow me to use S and P. Okay. So I hope that is all right. And of course, in the CSTR, the accumulation is, I will switch it off and switch it on. I hope it doesn't create problems. Let me see. Can you hear me still?
Yes, sir. Yes.
So it is V ds by dt, because V is the volume. This is the accumulation term. The accumulation term here, accumulation is V ds by dt is equal to, F S naught, and S naught is simply SF, because which is whatever is coming into the reactor. S naught is coming in and S is leaving. And I hope the volume is V and the flow rate is F. And F is, of course, the flow rate is the same. F is equal to F, because there's no change in flow rate. And the substrate enters at S naught and leaves at S out, which is just S. And the main argument of the CSTR is rather simple, which is that if it is an ideal CSTR, then S out is the same as S, which is the S here, right? Because it is well mixed, reactor. Because it is a well mixed reactor, therefore S out is the same as the S inside the reactor. So CSTR V ds by dt is equal to FSF minus V FS S out, which is the same as S minus, because substrate is getting converted, minus reaction. This is getting troublesome. Can you hear?
Yes, sir. Yes.
Yes. Yeah. So essentially, the CSTR equation is rather simple, and it essentially says that and if we divide by V, we could do per unit liter reaction kinetics. If we divide by V and do per unit liter reaction kinetics, then we can simply say ds by dt is equal to d S naught minus S minus reaction, where D is the dilution rate, which is defined as flow rate per unit volume. So it is per unit. So essentially, you are choosing the basis as 1 liter. The basis is 1 liter. So all of this is all familiar stuff. So I am going to go fast. Wherever it's not familiar, you please stop me. Okay.
Yes,
and therefore, yes. at steady state, this is 0. So we really have D S naught minus S is equal to reaction. Is the basic equation for a CSTR, which is quite different from the reaction for batch cultures. Now notice that this reaction is a function of S and not S naught. That's an important point to remember, because it is a function of S. It could be any function of S. It could be Ks as a simple first order reaction. It could well be K naught. If it's a zeroth order reaction, it could be simply equal to K naught. It could be equal to FKS. It could be equal to Ks lesser of N. It could be, as I pointed out just now, it could be Vmax S upon Km plus S, K plus S, or Km plus S, as we write it in. It could be anything. The point that is to be remembered is that it is a function of S, and S naught has no role in it. Because S naught falls here, this drop here immediately gets converted to S. So for as far as this reactor is concerned, it sees a concentration which is always equal to the outlet concentration, and that is the essential assumption of ideal CSTR. The ideality assumption. So we can then solve these equations. Let us solve it very quickly for some few cases. So essentially what we are saying is that at steady state we are at an ideal CSTR. We are saying D dilution rate S naught minus S is equal to, for first order, let us write it, for first order is equal to K into S, right? So the K value can be found out very simply, and what would be K equal to? K is so essentially we can say that D by K, or I mean usually people write it as D by K is equal to S upon S naught minus S, which is also equal to S upon P, because S is going to P, right? So the ratio of the dilution rates, and K is also first order reaction, so therefore both have units of time inverse, right? And therefore this is a dimensionless number. So essentially the proportion of dilution rate to this is the proportion of unconverted substrate to the amount of converted substrate, and that makes a lot of sense, right? So the higher, when the dilution rate is equal to the constant, then 50% will be converted. When it is say double of this, then when it is very high, then most of the substrate will be unconverted and a small amount of product will be formed. When D is very low, so if it is 0.1 of K, if D is equal to 0.1 K, for example, 90% will be converted, and so on and so forth. And so we can see that these are very simple reactions and simple ways to find out the value of K. The value of K can be found out by a simple, a fit of D versus SYP. And so a plot of D versus SYP, or rather actually, because we are plotting D and this is equal to, okay. And this is what, I mean, either we plot it like this or we plot it the other way around. These are all mirror images of each other. We can have this in the y-axis, and whatever line we get, straight line we get, should solve the problem. Should provide us data which then allows you to find out K or whatever. I don't know whether this is correct or not. ठीक था ये 1 upon K होगा इसका, तो ये slope अगर S by P versus ये होगा, ठीक है. So now for asymptotic reactions or nth order reactions, then what do you do? D S naught minus S is equal to K S square. For example, a second order reaction. And then of course your plots have to be carefully designed. You understand, right? D by K have to be plotted against S square upon S naught minus S.
Yes, sir.
To get the K value, right? And if it is an nth order reaction and you do not know N, then you are in even bigger trouble, because you have to write it as K S instead of N. And then you have to take log. So you have to take log and you have to say ln D plus ln whatever. What is this? Can you hear me?
Yes, sir.
Ln S naught minus S is equal to ln K plus ln S. And so then arranging these plots carefully so as to be able to find out both N and K is a tricky business, but not very difficult mathematically, much more difficult actually experimentally. Right. So the most common thing that we are interested in the ideal CSTR business is, of course, the asymptotic reaction that we were talking about just now. And so what is the asymptotic reaction? Can you all tell me? This is something which you all know, so I'm sort of, tell me please. Bataiye.
So Vm into S divided by K plus F.
Yeah, that's right. So what is my reaction kinetics? It is D S naught minus S is equal to, as I said, RS. This S, right, is equal to, as you rightly said, VMS, as in total reaction kinetics, would be Km plus S, right? And we can also therefore write it as, now remember, one of the things that we are interested in, for example, is X. What is X? X is fractional conversion, the product form per unit S naught. So X is nothing but S naught minus S, which is P, upon S naught. Is X is fractional conversion, right? You are familiar with all this stuff. So what do we get it in terms? Yeah. So this becomes, this first term here becomes D S naught X. Okay? Are you with me till now? That's obvious, right?
Yes,
and what is
yes.
S? And what is S is equal to? S is equal to, sorry, I'm sorry. S is equal to S naught 1 minus X. Right? Because, and P is equal to, obviously, P theoretically is equal to S naught into X, that is the amount converted. This is the amount of unconverted substrate, plus P naught if there was something coming in, but let us sort of assume that this is 0. Okay?
Yes, sir.
From this. Yeah, okay. So therefore we can write these kind of equations as D S naught X, ये ऊपर वाला, D S naught X is equal to Vm S, yeah, this is S naught, let us substitute this here, S naught 1 minus X upon Km plus, oh, this is crazy business. Can you hear?
Yes, sir. We can hear
Yes,
and see.
Yeah, yeah. So plus S naught 1 minus X, okay?
Yes, sir.
And this is a simple algebraic equation which you can now rearrange. I mean, you want to do Vm by D and you take all these terms here. So you write S naught X, you take this here, Km plus S naught 1 minus X upon S naught into 1 minus X is equal to Vm by D. So again, you have a very clear relationship and you can simplify this fraction a little bit you can simplify, but that's not really important. But what is important is that, again, you see at different dilution rates, these ratios will change depending on what is your Vmax and what is your K. And then you can sort of make, and I will leave this for you as an exercise. So how would you plot a graph where you can find out Km and Vmax from D? Of course, if you want to really, I mean, this is what we call the operational equation of a CSTR with rest reaction. Operative equations, you remember that all operative equations are written in terms of fractional conversions and operating variables and the constants. So S naught and X are the operational equations and Vmax and Km are the reaction parameters. Of course, it's far simpler. This is the operational equation, but when you want to find out Vmax and Km, then of course it is far easier to use this equation itself. With this is an easier equation to handle. This is an operational equation. I will now rub this out. You are all, I mean, these are all very simple algebra. And what you really want to do is that the operational equation is, you just write, just write it as D S naught minus S is equal to Vmax S upon Km plus X. Sorry, Vmax, this is something like R. Km plus S. और इसको आप simplify कर सकते हैं? Can you write it in terms of, say, D and Vmax? I mean, well, you can cross multiply it, but I mean, I can do an easier job of taking the inverse. ठीक है ना?
Yes, sir.
Shall I? This is a regular trouble that I'm now going to have. I hope you can hear me.
Yes, sir.
Yeah, I mean, you do your cross multiplication, and I want you to do this very simple exercise on your own. and the only way I can ensure is this to be that what is how will you find out Vmax and Km, and what is the relationship between these parameters? So of course, I mean, d s naught minus s into Km plus s is equal to Vmax s, right? And you can simplify this. What would you get, and how will you solve it? And so, what, for example, unlike for example, this is your operating equation, and now you need to write it in terms such that what would you plot is my question. What would you plot y versus x so that you can get some kind of line such that the slope and intercept tell you something about Vmax and Km, because these are the operating parameters. Are you getting this argument?
Yes, sir. But this will be like we can get after plotting we can get d, but like if we can get intercept and slope, then we can determine x and y. So that will be Vm and d, Vm and Km.
नहीं ऐसा नहीं होता, इतना सिंपल नहीं होगा. अरे भाई, I think I should do it. Okay. Let us sort of do it slowly. I mean, you people are delaying a lot. Okay, now let us then do it slowly. Let us say we have a first order reaction. d s naught minus s is equal to ks, right? So what do you plot? I mean, if you have only s naught and s, then d by k, as I said, is equal to s upon s naught minus s, right? So what is,
Yes.
so add a component of dividendo, add the numerator, add the so d plus k by d is equal to s plus s naught minus s. What is that equal to? S naught, right? Or rather, yes. I should have done the other way around. Sorry. I did the other way around. I should say s naught minus s plus s. So d upon, d upon k plus d is equal to s divided by s naught. Okay?
Yes, sir.
ठीक है, तो so therefore I can plot. I mean, so now this is your basic equation, operational equation. So your percentage conversion x is d upon k plus d. Okay, and in terms of the plot, for finding out k, you will have to plot d versus this. So for the plot, you will have to plot d versus s upon p and get a slope of k. Right, now for this equation here, how will you plot it? This is for first order, and how will you plot it for this kind of equation? You have d, so you have 1 upon d s naught minus s is equal to km upon vm 1 by s plus 1 by Vm. Okay? Are you getting this? I just reversed it. So you will plot 1 upon dP, which is this, versus 1 upon S. So this will be this, and this will be this, and your slope will be this, and your intercept will be this. ठीक है ना? अब क्लियर हो गए? ये सब आप लोगों का काम है, ये मेरा काम नहीं है. ठीक है? Is it all right? Hello?
Yes, sir.
Can you hear me?
So,
So really the operative equation for finding out this is that when you have data, So essentially, I mean, to make it very, very simple, this is how I do it for the MSc students, not for you guys, that when you have, this is the first and the last time I'm going to do this. Yeah, go ahead.
So if we plot this graph, since substrate concentration is in the denominator at very low concentrations of substrate,
Yeah.
like wouldn't there be errors while like if you
Yeah.
make
So
measurements?
the error analysis part I will teach in practicals. In the practical course, I will take. I did mention about optimization. So obviously these graphs are very dangerous to plot. So you have D and S data with you at different dilution rates. You are told that, you know, with a starting concentration of 10 grams per liter, I generated a fermenter run. I mean, CSTRs with 0.1, 0.2, 0.3, 0.4, etc., etc. And I got, say, you know, 0.5 grams and 0.8 grams and 1.5 grams and 3.4 grams. And this is my data. And this is S0. Now, from this data, please find out Vmax and K. This is my question. This is the actual quiz question. So the first easiest method would be to actually from this, and this is, as I said, told you, this is what I tell my my MSc students, that first I from here take the Excel sheet and extend it and plot here 1 by D S0 minus S. Which is easy enough. You can calculate these data points. Yeah.
Not hear you.
Sorry. मुझे आवाज नहीं आ रही. Shall I cut it out? Hello. 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 You can't hear me?
So we can.
No. वो बीच में I think I lost you and you lost me. Is it okay now? Hello.
Yes, sir.
It's okay. So obviously, from this data, you find out 1 upon D S0 minus S, which is this data. So you plot this, and that is a Y. You find this out in an Excel sheet. And then on the same Excel sheet, you plot 1 upon S, and then fit in a straight line between these 2 points. Now, this fitting of the straight line regression analysis is dangerous because of error associated with measurements. Now, you have to find out what is the error and where is the error coming from. For example, is your error in the measurement of S? So these are the questions which we will talk about later. Hello?
Yes, sir, we can hear you.
Yeah. Sorry, I keep asking this. This is a problem of my laptop, and I think they. So if you can hear me fine. So really, the idea is that such a plot of this matter versus this thing, in order to get a slope of Km by Vm and an intercept of 1 by Vm max. Now, this data can also be generated as y is equal to mx plus c. But remembering that this y and this x are not correlated in a linear fashion, they are correlated by this expression here. Now, if you want to do it properly and algebraically, then you need to say where is the error and is it proportional or not. For example, if your error is in measurement of S is measured with some amount of error, and D is a dilution rate, there is no significant error in the measurement of D, then all of S has to be written as, and so if there is and if the error in S is proportional to the S, for example, when you measure 10 grams, I mean, of course, if 10% error is too high, but let us say you have 10% error and your error in 10 grams is 1 gram, but your error in 1 gram is 0.1 gram. So if the S values are 0.5 and there's a 10% error, then it is actually 0.5 plus minus 0.05. And if it's 3.4 here, it is 3.4 plus minus 0.34. So the error in this case is proportional. In which case, this equation here, you will write D S0 minus S, because S0 has no error, S0 minus S1 plus E. Okay. And here you will write Vmax S into 1 plus E upon Km plus S 1 plus E, and then try to do a least square fit, because your error in measurement, and then you need to do an SS where you do DSS. I mean, the sum of squares is such that that error is minimized. This E has to be minimized, which I talked about in the practical class, and we will talk about this even more later on in the practical class. Here, let us not talk about error, because that is a practical issue here. So this kind of minimization of error is far better than minimizing the error with respect to this as y, the 1 upon this as y and 1 upon this as x. So obviously such plots are more dangerous, because they tend to not minimize the real error, but minimize the error between y versus x. Y is equal to mx plus c, and they try to minimize errors as y plus e, right? That is what you are essentially writing. But it is, the error is not 1 upon d S0 minus S plus e, plus minus e, right? It is not. It is actually, this is the error. So you are now minimizing this error, not this error, which you should have minimized. So that is the problem. Anyway, so let us come back to the basic point that, so this is how you plot CSTRs and data plots here, and I'm not going to sort of go too much into detail of this. This is something you would have done. So you have an nth order reaction. Nth order reaction, same thing. You'll have to now plot this as, this is equal to Ks Wisdom of n. So again, now what kind of plot will you make? So on the other, so these are the plots that you get, and you can then determine K and N, or these are the model parameters. The model parameters have to be found out from data which is given by D by S with error and least square fitting. But right now I'm just writing the actual equations for the CSTR. And the advantage with the CSTR model equations is that these are algebraic equations and easily amenable. So for example, in the batch reactor, the batch reactor was ds by dt is equal to Vmax S upon Km plus S. This is easy enough to handle. I mean, Km plus S ds upon S is good enough, right? Is equal to Vmax T. So here you are very simple. This is Km upon S. So you have an ln point, and this is S. So that's all right. And this is simply, I mean, I will solve the right hand side. You solve the left hand side. I always say that this is Vmt. And so this equation, the solution of this equation is often called the integral form of the Michaelis-Menten equation. Integral form. And this is simply nothing but ln of Km by S plus 1. So this is ln. This is just a constant K is equal to Vmax T. Okay. So this is the batch and this is the CSTR. Yeah. But really, yeah. Sorry, go ahead.
Nothing.
Any questions? Yeah. Okay. Because I want to wrap this up very quickly, because we want to get on to the. I mean, as I said, I'm always in a hurry. I'm always in a hurry because there are too many things to be covered and too little time. So remember that all these CSTRs, I wrote very cleverly ideal CSTR. Now, in actual engineering practice, you have non-ideal reactors. And I hope you are familiar with this, that you are familiar with the RTD, residence time distributions of ideal CSTRs.
Oh, yes,
so if you have an ideal CSTR, you would have, this is coming in, this is going out, perfect mixing. So at this point, if I give a pulse at time t is equal to 0, if I give a pulse pulse is provided, which is essentially what it is. A pulse is essentially a Dirac delta function. It is 0 at all points. It is at point 1 it is infinity, which is of course not practically true. This function in the limit is the Dirac delta function, right? And you have the output of this function can be easily found out by your material balance, because your material balance is dc, let us put it now again back to dc. dc by dt is equal to, there is no reaction taking place. At time t is equal to 0 plus 0 minus, it is at time t is equal to 0 plus, c becomes equal to c naught because of the pulse, right? Because this area is fixed and the Dirac delta function is essentially making this part go to 0, tend to 0, while the height tends to go to infinity. But the area remains a constant. Area is the amount of pulse that you have added. So the moment you have added a pulse, a certain area, that area gets reflected in the fact that at t is equal to 0 plus, c is equal to c naught. And so the basic material balance becomes dc by dt is equal to d, and this is c. And then water is coming in. So input is 0. So d into, this is plain water, let us say. So here input is c is equal to 0. So 0 minus c. So with the initial condition that at t is equal to 0, c is equal to c naught. Right? So the initial condition is t is equal to 0, c is equal to c naught, because at t is equal to 0 minus, it was 0, but at 0 plus, your concentration has gone to c naught because of this perfect mixing. And this is a rather simple equation to solve with this initial condition, which is c is equal to c naught e raised to the minus dt. And you're all familiar with this. And this is what is the graph that you obtain. And this is also the residence time distribution. So c versus t. So because all these particles got added at time t is equal to 0, therefore the fraction of particles which reside for time t, this is the plot of t versus c, is this. The fraction of particles which reside for this much amount of time is this area here. And the fraction of particles which reside for this much time is this area here. And the fraction of particles which reside for almost 0 time is this particle of area. Which really tells you that in a CSTR, the largest amount of particles reside for 0 time. Because there is no history. All particles enter and all particles have equal probability of going out, and therefore you have this exponential function which describes the RTD of a CSTR. All of you are familiar with this stuff? Yes?
Yes, sir.
Hello?
Oh, yes.
Yeah. So okay. If you're familiar, let me ask questions rather than asking this very vague question. The mean residence time will be given by T bar equal to integral each particle, the fraction of particles which reside for time t. So this is an average is equal to c naught e raised to the minus dt. ठीक है ना? 0 to infinity. And then you have to normalize this function. So this was the graph, right? So this was c naught. It starts at c naught and then goes down, and this is t, and this is the plot of c. Arey, kya hai ye? So this was c, and this is c naught. It starts at t is equal to 0. T is equal to 0. C is equal to c naught. And this is t going to infinity. So 0 to infinity, this divided by, and of course this area has to be normalized. So divided by t bar will be just this, right? C naught e raised to the minus dt. This has to be equal to 1, right? So you want to normalize it. So what is this integration? This is the mean time. This is the mean residence time. Correct? Am I all right? Am I making sense?
Yes, sir.
Yes, sir.
हाँ, तो ये होगा ना मीन, क्योंकि ये इतने particles, the amount of particles which reside for time t is given by this height into delta t. Into delta t. So the amount of particles which reside for time t is given by c naught e raised to the minus dt is the amount of into delta t is into t. These reside for time t. Summation over t is equal to 0 to infinity, which is this expression here. I was just jumping, right? So summation C naught e raised to minus dt delta t, which is the thickness of this thing, into delta t into dt, and this is the simply the summation of this whole function. The denominator is to normalize the function equal to 1. So you divide it by this. So this is the t bar. So what is this equal to? Hello.
Yes, sir.
हाँ बताइए. मैं ये जानना चाहता हूँ कि आप लोग सब बोलते हैं कि हाँ हमने पढ़ा हुआ है, तो मैं जानना चाहता हूँ कि आपने वाकई पढ़ा हुआ है कि नहीं. अगर पढ़ा हुआ है तो आपको 10 सेकंड लेना चाहिए आंसर देने में. So the mean residence time, the RTD is this. The RTD is this, and the mean residence time will be some time here, na? Which is the mean residence time. ये t mean होगा. तो ये t mean निकालने के लिए आपको ये आधा एरिया इधर होगा, आधा एरिया इधर होगा, है ना? So basically आप ये निकाल सकते हैं. And t mean is what? Hello, how many of you are there in the class?
Sir, will it be log 2 upon mu, something like that?
अरे भाई आप तो हर चीज में सेल्फ ग्रोथ मत किया करिए, है ना? बहुत कम लोग हैं आप लोग क्लास में, ठीक है भाई. अरे मीन रेसिडेंस टाइम रिएक्टर में क्या होता है? आप कॉम्प्लिकेटेड क्यों कर देते हैं? फ्लोरेट, अगर फ्लोरेट F है और वॉल्यूम V है तो मीन रेसिडेंस टाइम क्या होगा? हाँ
F by V.
अरे भाई मीन रेसिडेंस टाइम F by V कैसे होगा? V by A.
Sorry, sir. V by F. 1 by D.
Which is equal to 1 upon D. ठीक है ना? D के यूनिट्स टाइम इनवर्स है. भाई ये तो कॉमन सेंस है. आप लोग क्या कर रहे हैं? है ना? तो भाई आप लोग थोड़ा पढ़िए, मतलब आप लोग अब ये कहते हैं आप. So the RTD for an ideal CSTR is this, and the mean residence time is this, given by this expression, which is obviously equal to 1 by D from common sense again. But you can almost solve it by by parts, and this will come to the same thing, 0 to infinity. It's not a very difficult integration to do. Okay. Now, really the point that I'm trying to make is more complex, which is that to the extent that we are in trouble is that the RTD is like this. So the ideal CSTR has an RTD like this, but like this. But non-ideal reactors, as we increase non-ideality, we will keep on getting like this. I mean, this is highly non-ideal. This is very, very high. This is very slightly non-ideal. So as we get into this, so if you don't have this behavior, this is the ideal reactor, you will get non-ideality, which will give you graphs like this. And to the extent that graphs come like this, we have to make various models to where the model are essentially has an RTD which matches the experimental RTD. That is it. You're familiar with this basic argument? So essentially, I need to make models of my CSTR based on the RTD that I have got available from my actual experimental data by doing a pulse tracer experiment. I do a tracer experiment, a pulse tracer experiment, and from this pulse tracer element, I obtain an RTD. And if this RTD is perfectly like this, I have no trouble. It is close to ideal reactor. If it is like this, I may have some trouble. And as it goes like this, I have more and more trouble. And I need to make various models, which could be, which have enormous complexity. And I will not go into that. As and when we talk about it, we'll work on it. But the RTD has to match the experimental RTD. Of the model RTD, the model may have parameters. For example, the simplest example could be that I have 2 tanks in series to model a single poor mixing in a reactor. 2 tanks in series will always have this graph. 2 tanks in series as a model, 2 tank in series model is essentially will give you a graph like this. I hope you can make out, because now the first reactor output, both are ideal reactors. The first reactor output is like this, which is C naught e raised to minus dt. And so the second reactor input is C naught e raised to minus dt. So the input is changing as C naught e to the minus dt, and therefore what is the output? क्या होगा output? जरा बताइए. There is no reaction here. It is accumulation. dC by dt is equal to input minus output is equal to F naught F C naught e raised to of minus dt minus F, sorry, actually D, but because F by V है, minus D into C. All of you? Minus D into C out,
Yes,
which is the C that we are trying to model. This is the C we are trying to model. With the initial condition t is equal to 0, C is not equal to C naught. C is actually equal to 0. The initial condition is that at t is equal to 0, C is equal to 0. And this is your differential equation, which is not difficult to solve. And you can see that if it is 0, then this graph will be like this. It will rise and fall. No? Now, ये दो reactors के size आप क्या क्या चुनेंगे? If they were V1 and V2, इनके sizes क्या क्या चुनेंगे? जिससे कि आपका ये red line आपके experimental RTD के साथ match करे. And that is how you handle non-ideality. I mean, let me sort of mention, this is now getting complicated, but I will just mention it because I don't know the maths myself and it is very, very tedious. Let me sort of mention that any method to solve the output of a reactor, to sort of determine the output concentration of a reaction from RTD data. So for example, theoretically, I can say that even if it is a very complicated RTD like this one here, I can always say that I will integrate, I will simply say, can you hear me? Just doing some funny noises. Hello?
Yes, sir, we
we
can.
can.
So theoretically, I can say that I will check each section and I will divide it up into small sections, and each of these particles reside for this much time, this much time, this much time. And then I will sum it up and do an integration on the actual experimental RTD, and I will find out the percentage conversion. Right? You getting my argument? I can have an RTD, and from the RTD data, I can know that how many particles reside, what is the fraction of particles which reside for how much time in the reactor. And based on that, I can say, I can predict the percentage conversion, because this gets converted less, this gets converted more, this gets converted even more, and this gets converted the maximum, because this is the particle which is residing for the longest period of time. Now, and then I will sum up the percentage conversions and integrate over the whole thing to find out what is my output of the reactor. What is the final percentage conversion that I want to predict from the RTD data alone. Now, these predictions are only possible, and that's what I'm going to in with first order reactions. From the RTD data to directly predict conversions is possible when the reaction is first order. When it is complex order, it is not possible. I mean, it's just sort of mentioning this to you. I do not know whether you've been told this in RTD and your reaction engineering kinetics. Have you been told this thing, and has this been derived for you? Hello?
Yes, sir.
You are familiar with this, right? Good. So now you can see that we can find out conversions, and now let us quickly wrap it up by talking about the PFR. And the PFR essentially is nothing but I wanted to talk about another subject, but I think this is good enough. So PFR is nothing but the batch in time, right? The batch in time, because as the liquid flows in the reactor, as whatever S naught coming in and going out as S, at any given point of time, and we know the velocities. So at any point here, if we can treat this as a batch moving forward in time. So this batch here has resided for almost 0 time. This batch here has resided for time t, given by L by V, where L is the length of the reactor and V is the velocity, the average per unit area velocity, and T is this, and at this point T is equal to tau, which is nothing but the volume by F. So, and at this point, this is how much, and so we can simply look at the batch reaction kinetics and do the conversion kinetics here, right? And so PFR also you're familiar with, it is just batch by time. So we can find out the output S, sorry, not S naught, by finding out the time tau, for which it resides. And then using batch reactor kinetics, which is essentially dC by dt is equal to reaction. Great. So this can be done, and T here is nothing but T can be substituted as L by V. So L by V is the parameter instead of T, which is the same thing. Now the problem with this is that again, this is for ideal systems. Non-ideal systems, you will have some kind of diffusion. You will have some kind of diffusion or axial dispersion, and the axial dispersion amounts will depend on the Peclet number. Okay, आप लोगों ने पढ़ा हुआ है, बताइए क्या होता है Peclet number? Hello. UL by D, right? Where U is the average velocity, L is the length, and D is the axial dispersion coefficient. What is this? What is Peclet number? Hello? Can you hear me?
Yes, sir.
Sir, we can hear you.
Yeah. Yeah. So what is Peclet number? It is convective. It is the ratio of convective transport to
Diffusive.
नीचे वाला to diffusive transport. आप लोगों को याद है, भूल गए हैं, मतलब बेसिकली जल्दीबाजी में पढ़ा, ठीक है, doesn't matter. ठीक है. So as you have higher and higher Peclet number, your convective transport is higher. So the outlet profile, as you can see, that the outlet profile, inlet profile is a perfect peak. Sorry, the inlet to the is a perfect peak pulse, and the outlet profile is given by the RTD, which will be like this. So if you have very high Peclet number, then your profile will be like this. But if you have a bad Peclet number, you have a profile like this. Bad Peclet numbers will go like this. And as you can see, and this is where I want to prove this point to you, as you can see that the conversion will be poor when this spread is like this. Because remember that this set of particles is residing for less time and this set of particles is residing for more time. In very simple terms, the reaction rates are highest in the entry point of the PFR. Look at reaction rates. Look at, let me do it sort of without the maths. Let us look at the reaction rates. The reaction rates is V versus S for such reactions is like this. So at the entry of the PFR, at this point of entry, the reaction is this. Is my map and my speaking, does it match or is it a long delay?
Yes, sir.
So this entry point, आपका velocity ये है, और आपका यहाँ पे at this point the velocity somewhere here is the substrate concentration has fallen. So for the fact that this particle resides for very long time, now these particles, this is T, so these particles here are residing for much longer than average, but their extra conversion rates are much lesser because now the reaction rates are very low here. But these fellows who were getting converted at these values are now not getting enough time. They will also go out. So the fact that particles reside for different amounts of time leads to a lowering of the conversion amount in a PFR, in a plug flow reactor. Therefore, you will not get the same conversion as a batch reactor with the residence time of tau equal to T because of axial dispersion. Do you follow this argument? And the more the axial dispersion, the poorer is the conversion, the net conversion. Because the more there is axial dispersion, and obviously that makes sense because as we have this PFR becoming larger and larger, you are essentially reaching tank in series. As you know that that one of the models that we make for PFR with axial dispersion is tank in series model as well. And the number of tanks in series makes it sharper and sharper. And as you know that in a CSTR, the conversion rates are lower because the reaction is a function of S. Sorry, again, one last minute. So let me sort of end it by saying that you all know that in a CSTR, In a CSTR, the reaction rate is a function of S, which is the S out, the final concentration. While in a PFR in a batch, the V is a function of S, which is changing this S naught to S, right? And obviously the V is therefore higher and lesser in the beginning. While while in the batch, the reaction rate moves from here to here to here to here, and same way with PFR. In the CSTR, the reaction rate is always stuck at the last point. So always CSTRs will have poorer conversions when you have reaction kinetics given by such kind of things. Only when they are 0th order, something like this, will there be the same conversion. So CSTRs will always give poorer conversions, and therefore the PFR, non-ideal PFR with some amount of mixing and an outlet like this will always have poorer conversions than an ideal PFR. Are you okay with this? And as a matter of fact, you notice that the ideal CSTR will have the least conversion, and non-ideal CSTRs may have slightly higher conversions, but not that it is desired. There are other problems as well. So this wraps up the basic equations and the basic background, because when we talk of immobilized enzymes or column reactors, we will have to remember that what is a PFR, what is a CSTR, how to determine kinetic parameters. You're familiar with all this? I just wanted to revise this. We'll stop here unless you have questions. All this is, I thought or I assume, is known to you. Shall we stop here?
Yes, sir, we can stop here.
Okay, thank you very much. So,
thank you, sir.
Okay, yeah. Anybody wanted to ask something?
Yes, sir. Sir, I had a question about the course policy.
Yeah.
So, sir, you defined a separate policy for the lecture part and a separate one for the practical part, both for 100 marks.
Sir,
obviously. We will get a single grade. So, what will
you will get a single grade? Yeah, yeah, you will get a single grade.
Percentage of the like parts for are sort
25,
of like
25, 75 in terms of the weightage. 25, 75.
Okay, sir. Okay, sir. Okay, sir.
Obviously logical, right? 3 credits for the lectures and the course and 1 credit for the practicals. So that will be 25%. This will be 75%. Okay.
Okay, sir. And sir, about that question that you gave us.
हाँ, तो बताइए आंसर उसका क्या है? तो now the answer is obvious when I gave you the whole formula.
Yes, sir. Yes.
Think about it. As I mean, I will stop recording. But my point is that think